Do try. Let me click on this. You can move the hand off the screen and. All right, good morning, everybody. So let us start our day today. And the first lecture will be given by Jentsch from Brookhaven National Lab. He's going to tell us about far forward physics, the electron ion collider. For yours. All right, it's getting to the end of the workshop already, so I'm sure you guys are very energized at this point, right? No one's feeling tired or worn out. Perfect. All right, I'm Jentsch. I'm from Brookhaven Labs down the road. I normally don't put outlines in my talks, but given that this is not a talk and it's more of a long form type of thing, I think it's important to kind of give a scope for what we'll talk about. So today, I'll mostly talk about some physics topics that are colloquially referred to as far forward. You'll also hear them referred to as exclusive processes. I'll just describe what that means here in a minute. I'm an experimentalist, so most of this is going to come from the context of how we actually measure something. But ultimately, this is a biased discussion because I'm going to be giving examples that I find interesting or things that I've directly worked on. So this is not going to give you a full overview of everything that possibly exists. It's not going to necessarily have your favorite topic if you're working on this type of physics. But it is stuff that is actively under study for the EIC physics program. And then tomorrow I'll go more into my comfort zone and talk more about detectors because that's mostly what I work on. So tomorrow will be a lot more pictures. Today will be a lot more plots. So if you get through today, you get a prize tomorrow. Perfect. So I'll only briefly introduce the EPIC detector. I see stickers on a couple of people's laptops for EPIC already, so some of you know what it is. And this is only to introduce the idea of what far forward is, and then I'll talk about the detectors in a lot more detail tomorrow. So ultimately, the EPIC detector is pretty much a standard collider detector, although focused on DIS. It has kind of all the standard types of detectors you're going to find in these collider experiments, tracking detectors, calorimetry, things for particle identification. And ultimately, this is what a standard DAS collision might look like schematically. You have your scattered electron that gets kicked out and goes in the backward direction. Your proton beam or nucleus beam will go down the beam pipe, and then you'll have some particles that can be produced kind of in the mid or forward rapidity region. And the goal is to design something that can capture as much of the collision final states as you possibly can. But ultimately, the stuff that we care about is the stuff that actually doesn't hit the main detector. So for a lot of the physics processes that we want to study, the particles that we really care about just keep going down the beam pipe, and we have to try to measure them somehow, and that's not easy. And I'll discuss why that's not easy tomorrow, but ultimately, when I'm talking about far forward, this is really all I'm talking about is these final states where you have a product that doesn't end up in your main detector, and it makes detection quite challenging in a collider. In fixed target experiments, this is a little bit easier. So this is really all we're talking about, and the context for this, and you'll see how many physics processes actually fall under this category. But ultimately, these things are more generally defined as diffractive or exclusive final states. And we call them exclusive specifically because you want to measure everything in the final state. These events are very small. In general, you can have as few as 3 particles in the entire event. So it can make detection interesting because you're looking at basically an empty detector when you try to measure something. Diffractive events are generally referred to as just something with a so-called eta gap between them. So basically, you just have a large pseudo-rapidity gap between your final state products. A lot of the time, what you're trying to measure is the momentum transferred to the thing that you want to measure in the far forward region. And what's interesting about this is that these types of events, they might seem kind of rare, but Hera actually found that something like 15% of the total cross-section accounted for these so-called diffractive events, which is pretty large because if you think about what actually happens kinematically here, it's kind of like these particles are seeing all this energy in the center of mass frame, but a significant fraction of the time the proton just gets scattered and goes about its merry way. It doesn't break up. And protons are fairly complicated objects. For them not to break up is quite interesting simply because that's a lot of energy for it to be exchanged. And so we kind of think of the proton as a type of superhero here in the sense that a lot of the time it stays intact, goes down the beam pipe, and we can measure it and do something with it. So there's a number of final states that fall into this category. The stamp collection just labels a few things that I've at least had some interaction with over the last few years. There's things like deeply virtual Compton scattering, which is kind of one of the pillars of what we want to measure at the EIC. But over the last few years, as we've gotten a broader chunk of the community involved, especially from other areas outside of the HERA community, we've come up with all these new ideas of things that have always been on the table to measure, but they're now possible with the EIC, or maybe better done at the EIC than done previously. And these different stamp collections cover a range of topics. So you have things like proton spin, orbital angular momentum, which is something that's never been measured before. We also have 3D imaging that comes along with this. You can really image the spatial distribution of the partons inside the proton. But then we have all these other things, some of which actually interact a lot more with more fundamental nuclear physics. So things like the EMC effect or short-range correlations that you might recognize if you're more in the low energy regime of this world. So ultimately, there's a lot of physics that's covered by just this little tiny region of where you might measure something in the detector, and a lot of it is crucial for our understanding of nucleons and nuclei. You can find a lot of these things detailed in these very long, very exhausting reports that we've had to work on over the years. So the white paper was kind of the first one that came out in 2012. So the basic pillars of the EIC physics program are there. The EIC conceptual design report is really focused more on the machine, but the yellow report, which you see referred to very often in this community, was kind of our first attempt to broaden the physics program. So it went from a roughly 150-page report to a 1,000-page report that described the physics and detectors we might want for the EIC. So ultimately, the yellow report really expanded upon the physics program laid out in the white paper. And while our mission is to build the thing that actually does the white paper physics, we discovered during this yellow report process that we get a lot of things for free, which is really cool. So our physics program can be a lot broader than we hoped without having to build more fancy detectors. We can use what we already planned to build and have a lot more access to underlying physics. So for the overall physics goals, one of the first things that we really want to understand is how the proton obtains the spin that it gets. So the proton has a fixed spin of 1/2. We know this from our elementary physics and chemistry courses. But the question is, how does the stuff inside the proton somehow always give us that same 1/2 for the spin? There's contributions that come from the quarks, contributions that come from the polarization of the gluons, and then orbital angular momentum. And ultimately, we've learned in the past from DIS experiments that something like maybe 1/3 of that total contribution is coming from quarks, which was kind of a surprise because we generally think of the proton as a thing with 3 quarks in it. But as we know from higher energy experiments, the proton is actually in and of itself very complicated. And so we've already found with measurements at RIC, which don't have a large reach in X, but more than we had previously, we've been able to constrain what the value of delta G is for this contribution. And it's something that we've seen to be slightly above 0. So ultimately, there's a huge elephant in the room, and that's this orbital angular momentum component, which is likely quite large. But ultimately, it has no experimental constraints. You really need an electron ion collider to be able to put constraints on this. And we'll talk a little bit about how we access it in a little while here. This is a little bit of a lie because we can actually do some of this constraining using ultra-peripheral collisions with hadronic colliders. You're just much more constrained in phase space. So it's kind of a way to get a hint without getting the full picture. The other thing that's really interesting here, and something I won't really talk a lot about because it's not my area of expertise, but it is a very interesting thing, especially for folks who have already worked in the heavy ion world, is this idea of saturation. So one of the things that was found at HERA is that when you measure proton distribution functions, what you find is that the gluon density actually starts to drastically increase as you go to very low X. And there's a question of what happens to that gluon density, because there's 2 options. One is that the density saturates and you maintain your understanding of physics the way it is. The other option is that this distribution continues to grow and you eventually violate unitarity and you have some beyond standard model physics. That would be really cool. So ultimately, it's basically this balance of this process, which is very unique to QCD. You don't see this in QED, but in QCD, because the gluon can interact with itself, you can have these splittings of gluons. And there's a question of when the splitting is going on and you dump more energy into the proton, is there eventually a point where it starts to turn into a recombination process? And this is kind of a little pictorial view of the proton from high X to low X. And the idea is that at very low X, you now have a proton that's filled with pasta, which sounds really tasty, but it's actually not what it is. But ultimately, this is what the PDFs kind of look like, at least for one particular range in Q square. And this is this density growth that we're talking about. As you go to very low X, the gluon density grows drastically, and there's a real question of what actually happens to it, and we don't have an answer to it yet. And then the last thing that I'll kind of overview here, and I'll spend a lot more time on this because this is something that's most interesting to me, is how we actually identify the detailed structure of the partons inside the protons and nuclei. So ultimately, when we measure PDFs, we're really, talking about a family of distribution functions. But when we say PDF, people are generally referring to PDFs just dependent on X. But you can also measure PDFs that are dependent on other variables as well, including the transverse momentum and transverse position of the partons inside the proton. And so if you're looking at ones with transverse momentum, those are called TMDs. We won't talk a lot about those in detail, but I'll introduce them. And then talking about transverse position, we're usually talking about things that refer to this imaging program that we want to do at the EIC. And so in principle, all of these different things that I mentioned here can produce final states which are consistent with this far forward picture. And so you need the ability to measure these particles if you want to have access to all these different physics topics. So on the protonic imaging side of things, the kind of golden thing that everybody would want access to do everything we possibly could want is a Wigner distribution. You hear a lot of these, or these referred to a lot in condensed matter, but in our field, they're difficult because in principle, they're not really accessible experimentally, although there are some theorists who have some new ideas for this. But ultimately, what we generally look at are integrals over either the transverse position or over the transverse momentum of the partons. And that's where we get the so-called TMDs, which are the PDFs that are dependent on X and the transverse momentum. And then we get these so-called impact parameter distributions, which are more the spatial imaging side of things. And if you integrate over the momentum or the position in both of these things, you get to kind of what we normally colloquially refer to as just a standard PDF. So these are really just a standard parton density. Most of the PDFs that you hear referred to from things like HERA are generally referring to these types of PDFs, although all of these in principle are PDFs. So if you want to have more access to information, you can do all kinds of clever mathematics, including just doing Fourier transforms of the position space dependence that you get here and learn more about the distribution of the partons. But what's difficult here is that a lot of these things are very, very challenging to access experimentally. So most of the time what you do is you have a model that uses some of these pieces as input, you do integrals over those things and fit to the actual data that you have. So your data has to be very precise in order to learn anything. And that's one of the things EIC is trying to do. It's not really something where you're going to have all these massive discovery type things like you expect at the LHC, but instead you want very high precision for all of your data. So you'll hear the EIC referred to as a high luminosity machine, a precision machine. It's not the sexiest aspect of approaching physics. We want to discover something brand new and fantastic, but ultimately to learn stuff, we have to just take very precise measurements. And that's one of the key takeaways from a lot of the things we want to do is that many things we want to measure are not measuring something directly, but rather measuring something with high enough precision so an indirect fit can actually tell you something about the physics. These are some examples of what some of the various models can give you for TMDs and for impact parameter distributions. These are, once again, not things we measure. These come from specific models of these particular things. But ultimately, when we want to do a measurement, we have to have a process to start with. And so the simplest process we generally talk about here is deeply virtual Compton scattering. Ultimately, the main thing we care about is that this produces three particles in the final state: scattered electron, a real photon, and a scattered proton, and that's it. To do this imaging program, the main thing we need to be able to do is A, identify that the event was there, and then B, calculate the kinematics for the scattered proton, because that gives us the T that we want to do this imaging measurement. And so basically you're measuring a differential cross-section on the momentum transfer to be able to do this, and that's where you really require having good coverage of protons that are basically collinear with the beam to be able to do the physics. Ultimately, these things can be sensitive to these generalized parton distributions, which are related to these impact parameter distributions. But when we say sensitive to, it doesn't mean you're directly measuring them. It means that you have something that could be sensitive to a model of GPDs and teach you something about the underlying distribution of partons. This is an example of some of the measurements that were done at HERA, and these data look very, very beautiful when you consider the difficulty in measuring them. But then you look closely at the number of data points you have for each of the different bins. It's not very many. And so ultimately, it makes it really difficult. So one of the things here, for example, if you're looking at the DBCS cross-section as a function of Q square, you have two different shapes that you could have for the overall behavior of the cross-section. You have a so-called dipole model, and you have a GPD model here. There's also exponential fits. And what you find is that the chi-squares for these fits end up being quite similar. So you can't really differentiate them. And this is where the precision part of this comes in. If your precision is not high enough, and if your acceptance in your detector is not high enough, you're not really able to differentiate different fits that tell you something different about the underlying physics. So ultimately, what you want is an experiment that can give you both very high coverage for the kinematics of the scattered proton, and something that gives you enough statistics to where you have the ability to really differentiate between different models. And so ultimately, we're really building off of a physics program that Hera did and saying, well, we want to be able to extend what those capabilities were and go far beyond what we've done before, because where things currently stand, we don't have a lot of differentiating power for different models, and that's very challenging. And you hear this repeated in every single particle physics experiment in the world, right? We always want more and more and more data. So the goal here is not just to get more data for the sake of it, but really have a focused idea of what data we need and where we need it to actually extend our knowledge of the physics. And this is an example of what one actually does. So if you measure your cross-section in T from DVCS, this is just for a particular beam energy combination and for a fairly large integrated luminosity. You measure this T distribution, and literally all you're doing here is getting the proton, calculating its momentum, and calculating T, and then plotting it and scaling it by the luminosity. That's all this is. And you do a fit to this. In this case, it's an exponential fit. And the Fourier transform of that gives you this impact parameter distribution. So this tells you how the partons are distributed as a function of the impact parameter in the proton. What is hidden here is that you look at the number of bins here compared to what we had in these measurements. It's quite a significant increase in the number of bins that we have. This is still fairly optimistic, even for the EIC. So ultimately, what's really important here is that we have, a large coverage overall in T, especially down to very low T, and that we have enough statistics here to really constrain our fits. Getting something that looks like this is really non-trivial, but this is the goal, right? So we want to have enough statistics and enough physical coverage to get something that has this level of precision, so our theory friends can really help us to understand what's going on inside the proton. You can also extend this a little bit further and look at different aspects of partonic structure by not just constraining yourself to DVCS, where you have a photon in the final state, but also looking at vector meson production. So the vector meson production changes the scale that you have, but it also changes specifically what kinds of partons you're sampling. So in the case of the J-psi, you have direct access to gluons, of course, and then you have also access to understanding of charm production. But with lighter vector mesons, you can also look at different quark flavors that you're sensitive to inside the proton. There are challenges that come in with that too, especially experimental ones, but ultimately the goal is still the same. You want to identify what event you have, and you really care about measuring the kinematics for that scattered proton, because that gives you the best measurement of T. This is just kind of a collection of what different things you have access to with different vector mesons. Don't read the slide, too much in detail. It's really mostly to point out that the different vector meson program here gives you different access to partonic structure specifically. Like I said before, these types of slides can be a little bit misleading because it makes it look like you're directly measuring one of these GPDs. Ultimately, what you're really trying to do is measure things that are sensitive to a GPD model. That is the end of the day, what you actually have to physically do. One of the things that's also really important here that we won't talk a lot about, because polarized measurements are still rather challenging for us to do simulations with at the moment because of the generator side of things. But ultimately, you also care about the polarization aspect of things, and you can measure things like spin asymmetries, and that gives you some more sensitivity to the underlying GPDs. And ultimately, the really important part here is that if you want to get access to the orbital angular momentum component of the GPDs, or the actual orbital angular momentum aspect of spin, you really need polarized proton targets to do this. Right now, RHIC is the only polarized hadron machine in the world for a collider. And we're going to extend that capability for the EIC and really allow us to get access to this part of the physics program. And then the last thing I'll mention here on this is that when you look at the spin sum rule, as we talked about earlier, so you have your component from the quarks and your component from the gluons. For the orbital angular momentum component of this GPDE is the one that's normally seen as responsible for orbital angular momentum. You do actually have access to this in ultraperipheral collisions at RHIC or at the LHC. At RHIC, of course, because we have polarized collisions, we have real access to the spin asymmetries. I'm actually working in a measurement of this now. It's really freaking hard. It's a lot easier at the EIC. But it is something that in principle you can get access to in different collision systems, but the EIC is kinematically more favorable to do this. And to give you an idea of the phase space coverage that we'll have at the EIC for this type of measurement compared to previous ones, so all the little data points that you see on here are from various different experiments from Hera and also at JLab. And you can see that for all of the experiments at Hera and JLab, the fixed target one, so this is Hermes and the JLab experiments, they're all at very high X and low Q square. And then for the collider experiments at Hera, so Zeus and H1, they're kind of in this little strip of X and Q square. In principle, the EIC beam energies allow us to have access to a much broader set of kinematics that cover this kind of whole region of X and Q square. So, the whole idea with the EIC is that we want to have a machine that's versatile enough to go to low and high energy to access both low and high X. It's not as easy as that, as we're learning as we try to design the machine, but ultimately that is the goal. And so ultimately, with an increase in statistics and phase-space coverage, we can really fill in this region of phase space and have a much better understanding of the underlying physics. Okay, intermission. I've been talking a lot. This is my cat and dog. They're really cute. Take a minute to wake up. Now that I'm talking for a long time. Dog is a German Shepherd Schnauzer mix. Don't know how that happened. She's 40 pounds of pure heart and joy. This is my 15-year-old cat. She's really mean. We like her. Okay, moving on. So, talked about protons a bunch. I did not give you the full picture of the protons, but that's because I wanted to get to this because this is the stuff that I'm really interested in, and that's light nuclei. So, one of the things that has become a big area of interest for EIC physics in the last few years, especially as the collider community has really gotten to work a lot more in their community in fixed target, the JLab, is this idea of tagged deep inelastic scattering. So normally in a DIS experiment, you care mostly about the scattered electron. So if you hear inclusive measurement, that word usually means you measure the scattered electron very well, you get X and Q squared, you get a cross section. Tagged DIS means that once again, you're focusing on some far forward particle. In this case, you're looking at some spectator that comes from the breakup of the nucleus, or spectators in the case of a slightly heavier nucleus. And you're using that kinematic information to have a more differential cross-section that gives you more detailed access to underlying physics. But it drastically increases the difficulty experimentally. This has been done extensively in the fixed target world, but the fixed target world has limits on the kinematics. This is where the EIC can drastically improve things. And there's a laundry list of topics. I only name a few here. And one of the things that's really interesting is that for anyone who's been in the heavy ion world, one of the things we really don't fully understand, even remotely at this point, is the details of how nuclear modifications come in to access altered structure functions for your original nuclei, right? So you have a nucleus with lots of individual nucleons. Each of them has some structure function, but now it's been modified by being in a nucleus. By using light nuclei, we might be able to study the transition from essentially quasi-free nucleons to the initial modifications that you see to these structure functions. This has been the goal at JLab for quite a while, but with the EIC, with the extended kinematic coverage, it may be something we really have a full physics program where you can really do this. And I'll discuss kind of the approach that we've taken over the last few years to try and establish a possible physics program here. And it's all for free. None of this was in the original white paper. None of this was in the original physics plan. This is all something that's been developed in the last few years as the community came together to figure out how to build the EIC. So it's really awesome that the physics program can be extended without changing anything about the detector design. Although we changed a little bit about the detector design, but don't tell anybody. So for deuterons, that's the easiest one to start with. The idea is quite simple. Initially, our idea was to look at short-range correlation. This is something that's been studied extensively at JLab. It's usually more of a low-energy physics kind of thing. And ultimately, the idea is that when you have a nucleus that's got many nucleons in it, as it breaks up, it's very often that you see these correlations between pairs of nucleons. And it's kind of one of these things that's been seen for a long time, doesn't really have a full, firm understanding at the physics level. And so the first goal that we had was to take a deuteron and do studies of the tagged DIS capabilities experimentally to see how we can have access to this so-called short-range correlation region of kinematics. And so to do that, we used J-psi production off of the deuteron. So the idea is that you have your scattered electron come in, you have a Pomeron exchange that produces your J-psi. Your active nucleon receives, the momentum transfer that you want to measure normally, and then you have a spectator that's just along for the ride. So as this nucleus breaks up, the spectator just keeps on going, and this the nucleon that's been affected by the interaction is now going to have different kinematics. But ultimately, if you want to actually get a proper measure of T, in principle, you need to measure both of the particles in the final state, and that's not very trivial. And so the way we did this was by putting together a Monte Carlo called Beagle. Beagle was originally designed for heavy nuclear interactions, so it's actually quite complicated. It's basically a mashup of Pythia and Fluka and DPM jet and hoping it all kind of works together. And it mostly does. And the idea here is that, well, if we take the pieces of Beagle that are related to the hard interaction, which is the DIS part, and then we use a parameterization of the spectator kinematics that you have for the deuteron, because we actually have a lot of parameterizations for deuteron wave functions and spectator distributions, then we can kind of make a version of Beagle that allows us to study deuteron. That was exactly what we did. And so we took those Beagle events, we piped them through some full detector simulations about 4 years ago and said, oh, look, there's a cool physics program we can do here. And so the idea is that if you have, say, the neutron spectator case, which is the more favorable one, the neutron is basically just along for the ride. So the only kick it's going to have is basically from the Fermi motion or the actual nuclear configuration they were in inside the nucleus. So if it was a more strongly bound deuteron, that means the proton and neutron were really interacting with each other. When the breakup happens, the recoil the spectator gets is proportional to the amount of interaction they were having. Or you can have a situation which is more likely where they were quasi-free, they were weakly bound, the deuteron has a very low binding energy. And ultimately, if you are able to tag the kinematics of that neutron in the final state, you can figure out what distribution, or rather configuration, the deuteron nucleons actually had. And then if you also measure the proton in the final state, then you can reconstruct T. So the idea is that you'd have a separate T distribution for different values of the neutron momentum that allow you to look in different regions of the configurations for the deuteron. So you're literally imaging the partonic structure as a function of the nuclear configuration. And that's pretty awesome, because that means you can look at nuclear configurations where they're more weakly bound and see what the nucleon imaging actually looks like, and then do the same thing when they're more strongly bound and see how it's different. And that's one of the things we want to understand is, how does it become different? How does it change? And this kinematic access allows us to do that. Now, the Beagle Monte Carlo doesn't have the details of the actual understanding of the physics, right? We're trying to understand that ourselves. It's really just there to give us the distribution so we can see where our detectors happen to be. But it's a very promising physics program. And we took this a step further a little while later and said, okay, well, we know we have access to both of these things, but what can we actually really extract from it? And so the next thing we looked at was essentially doing Hera measurements, but with the deuteron. So ultimately, at Hera, it was an EP machine. Trying to measure structure functions of protons is kind of a given in an EP machine. You can just do inclusive cross sections, and you can get these very nice measurements of structure functions, which are basically just cross sections with very high precision. So you see most of these data points here have almost no discernible error bar, and that's reflective of the capabilities of Hera. But we've never been able to do anything similar to this for neutrons. Because how do you make a neutron beam in a collider? Well, you can stick it in a deuteron and accelerate the deuteron instead. And that was kind of the idea we had is, okay, if we have our deuteron, we have a beam of deuterons, we put it in the machine, are we able to kind of do the same type of measurement, but on the neutron, and try and get neutron structure functions and do studies of things like flavor separation? So this is ultimately the only way you can really do this. You can't make a beam of neutrons in a collider. You can only make that in some kind of a spallation source. And so ultimately, when you do this, the difficulty is now, because you're in a nucleus, now you have other effects that can pollute your understanding of the neutron structure. And so, of course, we always have access to inclusive measurements. You can do the same thing that Hera has always done, but if you do this with the nucleus, now you have to try and average out all the nuclear configurations. So those nucleons can be in any kind of configuration inside the deuteron, and you have to average over all those possible configurations. You're super susceptible to all of the underlying assumptions for that. But with a tagged measurement, this whole tagged EAS concept, you now can really understand what the internal configuration of those nucleons is, and have access to a situation where maybe the nucleons are essentially not interacting with each other, which is less difficult than you might think, because on average, once again, these are very weakly bound. The binding energy of the deuteron is a couple of MeV. It's not very much binding energy. This has been approached at JLab already, right? This is where this idea came from. We didn't come up with it magically out of thin air. But ultimately, the problem is that the kinematic coverage in a fixed target kinematic regime doesn't allow you to do this very well, because you can't get down to incredibly low PT. And so this measurement's been carried out before, but the cutout is intrinsically somewhere around 70 MeV. And if you want to do an extrapolation to an essentially free nucleon, you really need to get down to about 0. And so that's what the the EIC allows us to do. Because we're in a collider kinematic frame, you're really able to get down to arbitrarily low PT. And I'll show you what this does for the measurement here in just a moment. But the idea is that we can use a very simplistic approach where you basically take a property of the deuteron wave function plus the measurement of the cross-section as a function of PT. And then you can use the property of that wave function to perform an extrapolation with very small amounts of uncertainty if you're down to 0 PT, and get access to the neutron structure function. So this is kind of an outline of how this is done. So this is what the total cross-section looks like. This is the kind of standard flux factor that you get from Hera. You see this in all the Hera cross-section measurements. And in red is the stuff that you add when you add in the spectator information. So normally the cross-section would just be dependent on xq square and the angle of the electron. You normally integrate that out anyway, unless you're polarized. And the red stuff is the additional information that you get by adding in the spectator. So now you have all this additional kinematic information for the spectator that you can use to look at different regions of the configurations for the nucleons. So if you solve for the reduced cross-section for the deuteron, it has this property that the reduced cross-section is proportional to the reduced cross-section on the neutron itself, with the only information that you need from theory here being the pole for the deuteron spectral function. This comes directly from your parameterization of the wave function for the deuteron. And there's many, many papers on this that come from actually data-driven parameterizations. And so we know this part actually fairly well. So it's not really a major uncertainty, and it's something that you can control. And so basically, by just looking at the tagged cross-section for the deuteron, you gain access to the actual cross-section on one of the nucleons. And you can do this either for the neutron or the proton. I'll talk about why that's important in a minute, but that's the idea. You take your deuteron, you smash something into it, and you're able to access the information of the individual nucleons if you're careful. So the idea here with pole extrapolation is weirdly simple, which I was kind of surprised by. It was one of the first times the theorist explained something to me and I understood it, on the first try. Ultimately, all you're really doing is exploiting the behavior of the deuteron spectral function. This is the pole that I was talking about here. So if you extrapolate this pole to basically a situation where your nucleons are infinitely separated, this is by definition free nucleons. So these are your two nucleons. This is the way the kinematics are distributed between the two of them. This is what it might look like in a normal deuteron. And the extrapolation is basically taking you to a region of the phase space where they're infinitely separated and therefore free. And the best way to do that is by being in a situation for this actual physical deuteron where the transverse momentum between them is essentially zero. That's the experimental part that's really hard in fixed target, is getting to that region, because then the extrapolation is essentially trivial. And so ultimately, all you're really doing is extrapolating to a place where the PT square is equal to this value of AT, which is the position of the actual pole. And that allows you to get the structure function, or the F2 of the nucleon. What's really important here is that in a nucleus, you have the nuclear binding effects and final state interactions. And by definition, for the wave function, you do this pole extrapolation for these large size configurations, these effects are not present anymore. So it is truly a way to get access to the free structure by looking at a quasi-free nucleon experimentally. This is what the actual behavior of the pole looks like. And so in the red solid colors here, you have the actual spectral function. The dotted line is the pole. So the spectral function is just the distribution of the momentum for the spectator that comes from the wave function. And the whole point here is at the pole location, the spectral function and the pole function are equal to each other. That's exactly where we want to extrapolate to. And so ultimately, if you take the ratio of the spectral function and the pole, the actual behavior is essentially linear. So when we do our fitting to try and do the extrapolation, we can do just a linear fit. It makes it very easy to do the extrapolation. So experimentally, all we do is we take a tagged measurement. So this is actually using full simulations from Beagle all the way through detectors. You do a full measurement of the tagged DIS cross-section. So in this case, we're looking at tagging the proton in the final state because we want to look at the neutron. So the proton is the spectator, the neutron is the active nucleon. And you take that distribution, you multiply it by the inverse of the pole, and that gives you the thing that you can actually perform the extrapolation with. So in purple here, this is what you get by default out of Beagle with no detector information or smearing involved. And you can see that with a simple linear fit, the chi-square here is incredibly good, very much what we want to see. You're able to extract to the actual point where the nucleon is free and get the structure function for the nucleon. And I have in the backup the way we actually test to make sure the method is working. We basically make sure that we get back what we put into Beagle. We know what we put into Beagle. And so you can test right away that the extrapolation procedure does what you expect. The thing that we want to do is with the black boxes, which is with the actual detector aspects put in. And you can see in this case, when you're measuring the scattered proton, we can use tracking detectors. So our smearing is actually quite small. And so there would be a very small amount of unfolding you'd have to do to correct for the detector effects, and you'd be able to perform this extrapolation using a full measurement. And that's the whole goal. Now, we can validate this in Monte Carlo super easily, right? We know what we put into Beagle. So when we get something back out, we can see if they match each other, which they should. But you can't do that experimentally. And so ultimately, what you want to do is also do the same procedure measuring now the free proton structure. Now the neutron is the spectator. And you can do the same thing and see if you get the actual proton structure that you measure in EP. We measure the EP structure functions very straightforwardly in HERO. We'll do the same thing at the EIC. Experimentally, the difficulty here is that measuring neutrons is more difficult than measuring protons. And so that's part of what we have to work out now over the next few years. And some of it actually has already been worked out with a new design for the detector that's going to be used, and I'll talk about that tomorrow. But ultimately, that's the real experimental challenge here. We want to do the free proton extraction from the deuteron. Measuring the neutron is now your bottleneck. But ultimately, you can measure both the proton and neutron structure from a deuteron at the same time, same experiment, same set of detectors, have really strong control of your systematics and the process that you're going to use. And it's a really powerful tool to be able to do this measurement. So this is an example of what you actually get from this process. So this is really showing two different methods that we use to do this. So the star is the pole extrapolation method. Ultimately, what you want is for the circles and the stars to be right on top of each other. The reason they're not on top of each other is because of the way that we bin the analysis. So basically, we try to do it like it would be a real experimental analysis. And so this difference would be reflective of your systematic uncertainty in a real measurement. But this is the kind of precision that we can expect for this type of measurement. The error bars that you don't see here are because they're that small. And this is a very modest luminosity. It's a few inverse femtobarns, which is very much within the capabilities of the EIC. So these are the kinds of things that we see from the published HERA papers, and we can do the same thing at the EIC in principle for both the neutron and the proton, which is a brand new thing to be able to do both at the same time, and totally brand new for the neutron. It accesses a whole new world of physics for us. Now, going the other direction, now not looking at quasi-free nucleons, but now looking at when they're interacting more strongly, which is really the interesting transition that I really care about looking at. We can look at things like the EMC effect. This is an ongoing study, and it's ongoing mostly because we're too busy to finish it right now. The EMC effect is a multi-decadal puzzle. It's very similar to the spin puzzle that we have in the proton, although I think this is a more complicated one for us to understand. And the question basically is when you take a ratio of cross-section, so for those from the heavy ion community, this is essentially an RAA measurement as a function of X. If you take a ratio of cross-sections that you get from different nuclei scaled by the atomic mass number, where is this dip coming from? Why is it there? We see it across the board in all these different ratios for different nuclei. This is just one example. If you look at the paper that's here, there's many different examples of different nuclei that have been used. Where does that dip come from? Why is it there? And so what we are trying to establish now is, can we try and understand the EMC effect at the EIC, not by using various different nuclei. So right here, you see that the A is a stand-in for different nuclei here. So this is for carbon, but you see the same thing for many different nuclei, and that's how it was originally established. The question we wanted to ask is, well, can we just do this with the deuteron as a starting point? The deuteron has two nucleons in it. If those nucleons are really close together, their structure functions will start to be modified. You'll see nuclear effects. And the question is, are you sensitive enough to be able to separate those nuclear effects from things like final state interactions? And so this was kind of more of a, well, what could we do type of study? And it turned out to be more promising than we originally hoped. Ultimately, the main thing here that we care about is kind of pictorial representation. We normally see the nucleons distributed like this inside of a deuteron. That's why the binding energy is rather weak. For this type of study, we care about this less probable case where the nucleons are really strongly interacting. And now we're parameterizing this in terms of the so-called off-shellness. So if they're more off-shell, they're more strongly interacting. And so the parameter here is no longer T, but rather T prime, which is the virtuality, and it's still related to the kinematics of your individual spectator and your original deuteron. And so our question was, can we control some version of the EMC effect just using off-shellness without changing the collision system? Because if we could do all of this in a single collision system, it's way more feasible experimentally. And so it was a question, could we actually try to do this? And so what we did is we took Beagle, which we already had familiarity with from several studies, and we said, well, let's take a parameterization of this EMC effect in terms of this off-shellness, which already has some history in the literature, and try and mimic it in Beagle. So we're not putting any real physics in, we're just putting in the effect from the EMC effect to see if we can see it. And so that's what we did. We basically added in this faux EMC effect into Beagle, which is really only applicable in this higher X region where the EMC effect is seen, and then said, okay, now we see this weight distribution is now put in. What can we do experimentally with it? Can we actually see the effect and differentiate it from it not being there? So the way we tried to approach this was basically looking at a ratio of the same deuteron-reduced cross-section that we measured in the previous study, but looking at it in different regions of X. So at an X of 0.5, you're squarely in the region where the EMC effect is happening. An X of 0.2 is outside of the area where we put in the EMC effect, so we know it's not there. An X of 0.2, our Monte Carlo doesn't have it in there. And we also chose this region of X because it's ultimately in a region kind of between where you have shadowing and EMC, or anti-shadowing rather. And so by choosing X of 0.2, you kind of avoid any other types of effects that could be there realistically in the data. And the other thing here is that in our Beagle setup, we don't have final state interactions included. I'll talk about those in a minute. They're really the biggest complication in trying to understand this. And so what we did is we looked at that ratio measurement and said, if you look at that ratio measurement as a function of PT squared like we did previously, in black is what you have default from Beagle, so no EMC effect added whatsoever. And then in red is what you get when you add in this fake EMC effect. And our question was, okay, do we have enough separation power? That was the first thing. And we also looked at the full detector reconstruction. And of course, this is a ratio measurement, so it cancels out some of the detector aspects that are challenging. But the elephant in the room is this guy right here. 25 inverse femtobards is a huge integrated luminosity, especially for this beam energy. This beam energy at that luminosity is something that would take several years, if not many years, to be able to achieve. It's not easy. So basically we said for the case with the neutron spectator, we can't do it because we can't get the neutrons. They don't make it to the detector. And in the case of the proton spectator, which is what we're showing here, that looks all pretty and wonderful and happy, to get something that looks as pretty wonderful and happy requires an unrealistically high luminosity. But because the EIC is, intended to be this very versatile machine, we said, okay, let's try different beam energy. Do we still have access to the X region we care about? And it turns out we do. So by moving up to a 5 GeV electron and a 110 GeV per nucleon deuteron, which is a 220 GeV deuteron, you need almost a factor of 2 less luminosity. And at this beam energy, that luminosity is much more achievable because the machine itself will be able to deliver a higher luminosity at this beam energy. And so ultimately, what we concluded is that this measurement could very much be possible. You can do it at the same time that you're doing the measurement of the free neutron stuff. So in a single run or 2 runs of electron deuteron dedicated running at the EIC, you could have this massive access to a physics program that was never originally envisioned that studies both free nucleons and modifications to that nuclear structure. And that's pretty amazing because it doesn't require anything really fancy except the detectors we already planned to build. You can also have stronger coverage for different kinematic variables. And so I've been showing everything in terms of PT squared, but you can also look at the light cone momentum fraction, which is really just a longitudinal momentum. And at 1, that's basically when the longitudinal momentum between the 2 nucleons is the same. So they both have this, roughly 1/2 of the total momentum of the deuteron. As you move away from 1, that means 1 has more than the other of the total longitudinal momentum. And you see a very strong sensitivity between the black, which is without any of this EMC effect added in, and the red with it added in. So ultimately, you really should have access to this, with the big elephant in the room being the final state interactions. And we have some initial comparisons of this. They're in the backup. The reason I'm not showing them right now is because it could be a whole talk in and of itself. And there's lots of debate in the theory community about how you model final state interactions. But that's going to be the hardest part of this, is separating final state interactions from something that's really EMC effect. And we don't really have a solution for that yet. It was really more just to establish what the prospects were. So I'm running very short on time, so I'm not going to spend a lot more time on the helium-3 thing, except to say that helium-3 is something we'll be able to polarize on day 1.
Since we don't have a discussion section this evening, we have a free evening, we have a little bit more relaxed schedule, so don't want to rush too much.
Fantastic. Okay. So for helium-3, the reason it's interesting is because we will be able to polarize helium-3 on day 1 at the EIC. We already have the ability to do this. So it's part of the physics program already. So this allows you to get access to structured functions with polarized neutrons, which opens up some new physics. The main thing I'll say here is that experimentally, it's a bit more challenging because now you have 2 spectators in the final state. You have to measure in your FAR4 detectors, which makes things a lot more challenging. We did some simulations of this a few years ago, although they were missing a lot of the details we have now in the simulation. So it really needs to be done again with our modern understanding. But ultimately, the idea here is that you measure a spin asymmetry. And the main thing that's really challenging here is that you do have uncertainties on some of these other structured functions. So of course, F2N, we don't know F2N. That's one of the things we're talking about trying to measure with the deuteron. So you do have some challenging aspects of the measurement, but ultimately, experimentally, you do have access to polarized neutrons this way by using helium-3. And so this is an example of kind of the extraction that one could do for these spin asymmetries. But as I said, these were preliminary before we had the understanding of the detector we have now. So this is something that we really need to re-look at with our modern understanding of our detector setup. This is really more of a hint of what one could potentially do. The last thing I'll talk about is heavy nuclei. I'll talk about this fairly quickly. Heavy nuclei, for the program that we've been talking about, are rather challenging. So of course, with heavy nuclei, there's this lovely picture of the photon going in, scattering off of the parton and creating kind of this jet going out of the nucleus. It's not necessarily that simple. So the idea here is quite similar to protons. You still want to look at diffractive measurements, but now rather than having a single proton in the final state, you either have an intact nucleus in the coherent case, or a blasting apart of the nucleus with fragments going every which way down the beam pipe. That makes measurement a lot more challenging. But there's a lot of rich physics you could access here, but it's complicated and very difficult experimentally. One of the things that we originally wanted to do in the white paper was really be able to compare the incoherent and coherent distributions. And the way that you would do this, the nucleus itself, if it doesn't break up, it's truly collinear with the beam. It's so heavy that the momentum transfer it gets, that kick, is not enough to get it out of the beam envelope. So often, if you have a lead nucleus or a gold nucleus, you can give it a high momentum transfer, it'll just keep going straight down the beam pipe. You'll never see it in the detector. But the stuff that you get from the breakup of the nucleus, you can veto all of those events. You get some fragments that fly out every which way. You tag those events, and the ones that you have left over, you assume are the coherent ones. That part is necessarily the easiest part, weirdly enough, tagging all those incoherent events, which is challenging in and of itself. And then you have access to in principle, the coherent cross-section. The idea here originally was that you could then look at different models that you have for saturation, look at differences in what you have for the production of the coherent cross-section, and use that to have sensitivity to saturation. And basically perform the exact same type of thing we do for DBCS, where you take your T distribution, your cross-section, do a Fourier transform, and you get back your impact parameter distribution. In this case, this is a very simple study where they basically just put in a Wood-Saxon distribution, or in this case, this distribution from Sartre, and tried to see if they could get back what they put in. And sure, you can if you have this cross-section very well measured. The difficult thing here that I'm not going to really discuss in a lot of detail because it's a little bit more controversial now is the actual measurement of this T distribution. So let's say you veto all of the incoherent events. You know for sure your sample is only the coherent ones. You still have to measure T. You don't have the nucleus in the final state like we do in the proton case. In the proton case, you directly tag the proton, you measure T, you get this cross-section. For a heavy nucleus, you don't have that. So you have to measure it using the other products, and your resolution becomes very poor. And so getting access to this clean measurement of these dips is incredibly challenging experimentally. So this program is one that has a lot of interest in the community, but we're still trying to figure out how we really do this experimentally with our renewed understanding of our detector capabilities. Okay, a lot of ground, biased introduction, stuff that I'm interested in. This is not the only stuff. There's a lot going on. Right now, we're working on the technical design report for the EPIC detector. By definition, that report is mostly focused on the detector. But if you're interested in the physics, our collaboration is also working on putting together a much broader document that covers basically any physics topic one would want to try and measure. That's where a lot of the deuteron stuff I've been talking about would end up going. It wouldn't go in the actual TDR. The EIC community is growing and tired because there's not a lot of us working on a lot of these things. So if you're interested, this is really the time to get involved. Even if you can only spend an hour a week on something, maybe you discover something interesting that we didn't think of before that helps us understand how we need to, adjust our detector approach or something like that. So if you have questions about any of this, if anything of this was even a little bit interesting to you and you want to learn more about it, please email me, come to some of our meetings, they're all open, and see how you can get involved. So tomorrow I'll talk more about the detectors and really how we actually physically do this and all the challenges, which are legion. So thank you.
Questions or comments?
If you have theory questions, ask Fred or Alexei.
So back to your plot about DVCS and about the number of bins. One of the issues with DVCS is that you actually get the moment of the GP, the first moment of the GP. So X dependence is integrated out. So I would assume that small number of bins is the reason why there's the inverse problem.
Well, that's part of it. So the small number of bins is less of an issue than the coverage of those bins. So what I don't show in this picture, if you go in the white paper, you'll see different versions of this Fourier transform with different types of detector acceptance, for example. So if your low PT detector acceptance is bad, so if your detector can't get close enough to the beam to get those protons that are at low scattering angle, you basically have a very limited understanding of the normalization of this distribution. So the error band on this across the board blows up vertically, and you can't identify where the normalization should be. On the opposite end of the spectrum, if you don't have good coverage at high T, it gives you basically no capability to differentiate the shape that you have. So an exponential versus a dipole, for example. So it's not just about the number of bins, it's about how much coverage you have at low and high PT. And then your overall luminosity becomes a lot more important for things like spin asymmetry measurements. Because normally what you would do is you'd have some number of bins in T, and for every T bin, you would measure the phi distribution, for example. And that then takes whatever number of T bins you have and breaks them up further, right? Something like 8 or 12 bins in phi. So if your luminosity is not high enough, that makes that measurement very difficult. So polarized measurements become very challenging. And if your acceptance is not good across the board, it makes it really challenging to get something as pretty as this. Those are the main things that matter. You can actually have, a fairly small number of bins here. In fact, my supervisor says very often, this is an insane number of bins to use because you don't really need all the bins as long as the coverage is very good. You could probably do something more like 10 or 15 bins here and still do perfectly well at being able to do the fits because ultimately the errors and the coverage are what matter most.
Just a quick follow-up then, is it possible that processes that directly measure GPDs might result in better coverage?
From my understanding, there are no processes that directly measure GPDs.
But they're fairly newer, they're experimentally fairly, theoretically fairly new.
Okay. I know nothing about them, so I can't comment on whether or not you'd be able to do that. Ultimately, I mean, for this particular set of data points, this is 10 inverse femtobarns, which is fairly modest for the EIC energy, right? I mean, we originally were hoping with our luminosity for the EIC to easily reach 50 to 100 inverse femtobarns in a year. Even with some of the more conservative estimates for the machines running, 10 is still very achievable. And you can see for this, the error bars are quite small. But what I'm hiding from you is that this is only one bin, an X and Q square. The issue is that when you look in different regions of X and Q square, especially at high X, you become really challenged if your luminosity is low. So if you want something that has direct access to GPDs, I imagine you'll have similar kinds of problems, right? You not only care about the overall amount of data that you have, but what your kinematic coverage ends up being. That's why we have different beam energies too. So if you want high X, for example, this beam energy is not ideal. You want a lower beam energy if you want high X. And in that case, the luminosity is more difficult.
For the EMC effect, why are you only looking at deuterium? Because normally it's the ratio with the ion on top.
Because the idea was that we were trying to approach it not using that ratio approach. So the idea that we had with this was we know we can measure the EMC effect using different nuclei, and in principle, the EIC can accelerate whatever nuclei we want. Rick can already do this. But the problem is that when you try and make a beam request for an experimental program at Rick, lots of people are going to fight with you about your beam request. And getting beam time for something that's really niche is very challenging. So our thinking was, okay, we're 10 years before, right? We're trying to think about these things now because we know how difficult it is now at Rick. So for me, I want PA running at Rick. We get a tiny fraction of time for PA right now, even though it would be really helpful for the EIC program. Extrapolating to the future, it'll be just as difficult. So our idea was, well, if we can do something with only a single nucleus and we get this whole physics program out of it, we have a much higher chance of being able to achieve the program because we can run those beam configurations longer. That was our idea. And we were just seeing if it was feasible. It could be, but the final state interactions part is the really challenging part. It is not the conventional way the EMC effect is measured, for sure.
So since there are heavy ions, you still can measure the EMC effect using the heavy ions at the EIC.
Yeah, you can still do the same kinds of measurements you want. The kinematic coverage is going to be different than what it has been in places like JLab. And of course, EMC effect's a high X phenomenon, and EIC is a higher energy machine. So you're going the opposite direction in terms of X coverage. So that's part of the challenge here too, is getting high enough in X while still maintaining a high enough luminosity. Low beam energies generally mean lower luminosity. So you have to try to find that happy balance, which is one of the things we tried to establish. So it's an unconventional approach.
Slide number 30.
Mhm.
When you say about the spin of the proton, you have the valence quark and the gluon contribution and also the orbital angle momentum contribution. But, how about the anti-quark and the C-quark contribution?
I mean, in principle, it's the same kind of thing. It just depends on what species you have in the final state, what quarks you're accessing. So that's the way you control the different quark species is by looking at vector mesons, for example. The challenge there, of course, is that you have different uncertainties that come in on those measurements because the vector meson part now adds its own uncertainty and experimental challenge. But if you want to access different quark flavors or anti-quarks, you need to use different vector mesons in the final state. That's the main way to do it. And there are arguments about how well you can actually do that. But that's not my argument. I'm not a theorist. I just say if we can measure it.
Other questions? So let's thank Alex once again.
Have a good break. And again, we can have water in here, so you can bring the sparkling water in here afterwards if you like. We'll pick up at 10:30.